Okay, so we should be. Any questions so far on like hormone-sensitive lipase? So let's go through an example of this. So this is what happens when a person does, let's say, a workout, and we'll talk about what kind of workout in a minute. But so far, that's some great YouTube. Okay, there we go. So keep in mind what's happening here. This is hormone-sensitive lipase, and this is a key enzyme for providing energy when a person's doing exercise. So it is activated. Remember, we talked about this in a couple different ways. And so what happens during exercise? So these are from an experiment on an exercising population. And during rest, it's free fatty acids, and this is in millimolar. Class today, and you decide, oh, I'm going to work out before I go home and look through my 328 notes again. You go into the health center. There's a grad student in there, and they're like, "We'll give you $25 cash right now if you're interested in being in my thesis research project. And in order to do that, I just need you to sign this form." You're like, "I'll sign anything." So you sign it, and then there's some things in there that you probably should have caught, but you didn't. You got on the bike, and they basically are like, "Okay, have you fasted?" And you said, "Yeah, I haven't eaten for quite a while." So they'll take an initial value and they'll say, "Okay, before you start, we're going to take this blood sample." And this person or she measures your free fatty acids and sees they are 0.43 millimolar. Does that mean anything? Not really, because that's an absolute amount that we were going to look at that in relative amounts in a second. And then they do your glucagon and your epinephrine. And then they say, "Okay, start pedaling." And you're pedaling away, and you're like, "Okay," and you forgot to ask them how long this is going to take. Well, 40 minutes in, you're just getting warmed up, and they're like, "Okay, we're going to take another blood sample." So they take a blood sample, and they see that this went from 0.43 to 0.66. Is that a lot? Right? So you think, I don't know how much that is. So let's look at relative amounts. I don't know, that millimole, that seems like not very much. Look, it's about 50% higher, right? So it's gone up quite a bit if you look at it that way. Right? How about this? Would you expect glucagon to go up? Why or why not? Who says yes? Okay. Who says, no, probably not? It's a risk, but sometimes the reward is worth it, right? So we had a gentleman in the back that weighed in on that one, so he was right. The rest of you were not. Didn't go up, and you could probably argue, well, at that point, 40 minutes in, your blood glucose might not have changed very much. Why or why not? So you fasted, you maybe started a relatively low blood glucose anyway. What's maintaining blood glucose at this point?
Liver stores?
Maybe liver stores, glycogenolysis, right? Is that a possibility? Well, let's see. What about epinephrine? Would you think it goes up? It's stimulated by the physical activity. This is going to be stimulated by blood glucose changes, right? This one, should we play this again? Who says up? Anyway, this is up significantly. So it's gone up. Now we're not measuring blood glucose, and to be honest, at this point in this type of exercise, blood glucose is probably not going to change much. You'll understand why in a second. Okay? But you can look at this and go, oh, well, maybe the epinephrine is stimulation, and it's helping to maintain blood glucose, right? How's it doing that? Epinephrine goes into the blood. How can we maintain blood glucose? Right? So as epinephrine is released, it can stimulate hepatic glycogenolysis. Remember that? So it works in the liver, and it can actually stimulate that. So that could be one of the things that's happening here. Okay? So now we're 40 minutes in. Hour and a half. You didn't realize it, but they strapped you to the bike. And you're still pedaling at this point, and they have no clock, so they're going, how long have I been on there? Like 15 minutes. It's only been 90, so you're on here an hour and a half. What's happening with these guys and why? Free fatty acids, up or down? Up. Right? Epinephrine's in the blood. Epinephrine is stimulating hormone-sensitive lipase. Free fatty acids are now significantly flowing from adipose tissue into the blood. So in this case, they could be going from, let's say, the abdominal region through the blood, attaching to albumin, running down their concentration gradient because they're starting to go up in the blood. They're going to start running into tissues. Tissue that needs them is the exercising tissue. So they could be going into your leg muscles and providing an energy source at this point. They've gone up quite a bit. They've doubled. Okay? Glucagon has gone up. It's 400 something at this point. Epinephrine's gone up significantly. All right, not done yet. 2 hours. What would you expect to happen here? Free fatty acids. Still going up. They're accumulating in the blood. Some of them are going into the tissues, but they're being released at a rate that they're still accumulating in the blood. Glucagon now is significantly increasing. It's helping to regulate blood glucose. Blood glucose is dropping. Glucagon's trying to keep it up. And epinephrine continues to elevate. Providing fuel sources, right?
For only $25.
I know, yeah, it's probably what you're thinking right now. You're like, wow, that's nothing. How did this project ever get approved? You're not done yet. You guys are still going. You just get warmed up. This is what you do all the time. 180 minutes, 3 hours. What about free fatty acids? That's it. How much did this go up? Approximately 5-fold. Significant energy source at that point. Is this high intensity exercise? Why or why not? Probably not real high intensity because you could do it for 3 hours. So in that scenario, oxygen is probably not limiting. You can burn fat under that scenario. So it's got a combination of glucose and free fatty acids that are the main energy sources. But at this point, going in that type of exercise, the free fatty acids become more and more of an important energy source. Okay? Now, you get off the bike, take your $25, right? You crawl or walk away from whatever, right? And what happens to these now? Yeah, they continue to be oxidized. Have you ever heard that? Fat oxidation after your exercise continues. So all those free fatty acids in the blood can continue to run into cells and be oxidized. Okay? At that point, obviously, energy expenditure rate is higher than it was before. And it'll continue to run into those tissues until it basically equilibrates back down to kind of a fasting value that it was before. These hormones will relatively quickly start returning to normal. And then it's the activation of hormone-sensitive lipase is no longer as active. Now, if you drink a carbohydrate, what happens to hormone-sensitive lipase?
It goes down.
Its activity goes down because if you drink carbohydrate, insulin goes up, and that inactivates hormone-sensitive lipase. Is that a bad thing? In that case, not really. It's important that that carbohydrate's there to restore muscle glycogen, and at this point, that's not considered to be a bad thing if hormone-sensitive lipase is inactivated. So that's kind of an example of how important this enzyme is during certain types of exercise. Not that it's only activated during exercise, because it's also activated during fasting, but that's one of the reasons why that fat is such a good energy source, because you can continue to do this for a long period of time. The fat's not going to be the limiting factor in general. Okay? And remember that enzyme is throughout lots of tissues, but especially in fat cells. Okay? So now let's think of it this way. All these free fatty acids that are now in the blood, now let's kind of follow them and see how they actually provide energy for all of this. We said, for example, they're going to be going from adipose tissue through the blood to a tissue that needs that energy. So how do we use the fatty acids for energy? Well, they can be oxidized to produce FADH2, NADH, and acetyl-CoA. We'll look at that in a second. And we know this probably, right? Per weight, fatty acid oxidation yields more ATP than glucose does. I'll kind of tell you how. Beta oxidation is the major pathway of oxidizing fatty acids for energy. Beta oxidation occurs in the mitochondria. And why is it important that it takes place in the mitochondria? Yeah, ETC's there. So these contain electrons that have taken electrons from those fatty acids. And that's occurring inside the mitochondrial matrix. So now these molecules can provide electrons to ETC. You're also getting acetyl-CoA for Krebs cycle. So part of those fatty acids are going through Krebs cycle. They're starting as acetyl-CoA. So let's kind of work out a little bit. Let's think about what's happening kind of on both levels. What's happening in the overall system in our body, and also what's happening in the cell. So let's say, for example, this is a fat cell. Here's our triglyceride droplet. And here's hormone-sensitive lipase. And we're going to say the fatty acids go into the blood. And they bind albumin. Now let's say this albumin transports this fatty acid to a muscle cell. Fatty acid can dissociate from the albumin and go inside the muscle cell. That fatty acid is then activated. And when we talked about reassembly of lipids in the enterocytes, we said that fatty acid has to first combine with coenzyme A, and then it can be added for other molecules. In this case, similar process. Coenzyme A is added to the fatty acid by fatty acyl-CoA synthetase. That enzyme needs energy to do that, so it's an energy-dependent step. How many ATP are required? 2 ATP equivalents, because it's going from ATP to AMP. So that's 2 ATP equivalents. Okay, because in order to go backwards, we go AMP to ADP, ADP to ATP. So it's 2 ATP. Okay, so the fatty acid enters cells. It's activated before it can be oxidized. So the activation means adding CoA. That occurs in the cytosol. And the CoA is essential for that fatty acid to be transferred into the mitochondria. That's why it has to be activated. So now, so our CoA is now attached. So if this is the muscle fiber, this is a mitochondria inside the muscle cell. That's where that fatty acid is going. Now it's got a CoA attached. Can that CoA go across that membrane? Are there any examples where we set up? This molecule has CoA, can't go across that mitochondrial intermembrane. Acetyl-CoA. So CoA doesn't go across, but the fatty acid needs to. So if we take that in mind, this is where we are. Here's the intermembrane space. Here's the matrix. So we're talking about a reaction that takes place right here, across that mitochondrial intermembrane. We said very stringent. Only certain molecules can go through, and they need transporters. So there's a transport system for fatty acids. And that's what's shown right here. So essentially what happens is this fatty acyl-CoA goes to that mitochondrial intermembrane. The fatty acid goes through, CoA does not. And I don't have enough room to show it on here, but if we could expand that intermembrane and look at it in this way, we can see that the transport molecule is carnitine. Have you ever heard of that molecule before? Carnitine. We make carnitine. So does GNC and bodybuilding.com and lots of places like that. They will say, consume the supplement of carnitine because it's crucial for fat oxidation. Is that true? Carnitine is, but not your supplement. Okay, so it's a required part for this, but generally we make adequate amounts. It's generally not a rate-limiting factor. But that's what the carnitine is doing. It's kind of it's a transporter to go across that membrane. And there's 2 enzymes that are involved in this process. We don't have to know those. But the carnitine replaces the CoA. So now this fatty acid with carnitine attached goes from the inside of the outer part of this membrane to the other side of that membrane. And on the other side of the membrane, carnitine is removed and CoA is added. So in this case, what happens is you end up with fatty acyl-CoA in the matrix because carnitine helped it get across. CoA is in the matrix. It replaces carnitine as the fatty acid comes out of that membrane. Got that? Does that make sense? There's more detailed, a little bit more confusing diagrams that I shy away from, but that's essentially what happens. So carnitine is needed to transfer the fatty acids into the mitochondria. Carnitine is a very small molecule. It's made from 3 amino acids. It's essentially a binding site for those enzymes. Those enzymes are called Cat1 and Cat2. Carnitine acetyltransferase 1, carnitine acetyltransferase 2. They basically, one enzyme does this, pushes off CoA, adds carnitine. The other enzyme does the opposite, replaces carnitine with CoA. So that's all that's showing.
If CoA can't get into the matrix, like why is it in the matrix waiting to add back on?
It's made in there.
It's just made.
Yeah, the matrix. So it's the same, as you go from pyruvate to acetyl-CoA, it's essentially pyruvate converts to acetate and CoA is added. So it's CoA. So it's CoA in that matrix. Yep. But now what it does is it essentially traps it. So it would take an enzyme in order to get that out. Now, is this very common? Is this an important way that we get energy? Absolutely. I mean, if we look at the numbers, fatty acids are a big energy source for us, and this is how they're oxidized. They go into the matrix. And the reason I'm saying this is there's some data that indicates, a lot of data that indicates, when a person starts becoming insulin resistant and they're not using as much glucose as they should be able to, and glucose is staying in the blood, they rely more and more on fat oxidation. Unfortunately, this system can be overwhelmed, and these weird kind of fatty acid products start accumulating in the cells. And there is a relationship between those incompletely oxidized fatty acids and risk of type 2 diabetes. So it's important that we can do this process efficiently, because it's a significant process. And even though we need carnitine, carnitine is typically not the rate limiting step. So this happens all the time. Every time you're oxidizing fat, like right now, fatty acids are in your blood, moving from one tissue to another and going into the mitochondrial matrix in the cells that are going to use them.
Since you said we're making up, what happens when you take the supplements? What happens to that?
It's a nitrogen-containing compound. So some of it's going to go into the liver and kind of go through a nitrogen pathway where the nitrogen's separated from the carnitine. It's very unlikely that it's going to enhance fat oxidation because it's typically not limited. It's not harmful. I wouldn't say it's harmful. I'd say it's probably just not something a person needs to take. So, good question. I'd say there's probably not much of a downside, but not really an upside. Or our body can break it down. So let's start talking about this process. You guys have talked about this before, so some of this is going to be review. So this is mitochondrial beta oxidation. Now we're going to continue on with the metabolism of that fatty acid inside the matrix. So just so we can kind of see this, I have this listed in steps. So step 1, we're saying that's the activation of the fatty acid, where it goes through the cytosol, gets a CoA. That allows transfer into the matrix. Step 1 of beta oxidation, remember this? No? It's basically oxidation, hydration, oxidation, cleavage. Ring a bell? Okay. It will in a second. It'll just come flooding back. Okay. Or not. So here are the steps. Up at the top, sorry, that's a little bit cut off. That's a fatty acid. It's got CoA attached. Name that fatty acid. Palmitate with CoA attached. So the CoA is attached, so we call it palmitoyl CoA. All that means is palmitate, CoA attached. How many carbons in palmitate? 16. Very common fatty acid in the blood. It's a commonly made fatty acid in our tissues, commonly in our diet, common fatty acid that's stored. So it's a good example. First step is when palmitoyl-CoA, and you can kind of see its structure. Right? Palmitoyl-CoA is saturated, which means saturated with hydrogens. And that's important because that means it has more electrons. So this is shorthand. Here's our methyl group. 12 methylene groups, CH2s. So long chain fatty acids, saturated. And then here's our CoA. In the first oxidation step, the enzyme, and you don't have to remember the enzymes, but the enzyme is called acyl-CoA dehydrogenase, pulls off hydrogens, as its name implies. What does it do with the hydrogens? Adds them to FAD. So you'll learn about this in 329, but FAD is derived from riboflavin, remember? And it is a coenzyme. In other words, an enzyme will basically use FAD to accept hydrogens. That's why it's there. So this enzyme, dehydrogenase, takes 2 hydrogens from the fatty acid, adds them to FAD. So now you have FADH2. Now the enzyme can deliver that FADH2 as a source of electrons to ETC. Okay? So that's step 1, oxidation.
Could you repeat that after an enzyme will use?
FAD is a coenzyme. Right? We've talked about that before? Like, let's say this is an enzyme. Here's my very good at drawing. There's an enzyme. An enzyme will essentially place FAD near its active site. So now when the fatty acid is bound by that enzyme, the enzyme pulls off hydrogens and converts this to FADH2. It's pulled off electrons. And now the enzyme can release this, and the FADH2 is oxidized through ETC. Okay? Now, and you can look at the structure and see what happened here. CH2CH2, if we look at that part of the molecule, now there's a single hydrogen, not 2. So the hydrogens came off. Now we have a double bond. Now it's hydrated. So a water molecule is added in that area of the molecule. So an OH is added here, and the other hydrogen is added here. So it's hydrated. That allows it to be oxidized again. So a second dehydrogenase pulls off 2 electrons, adds them to NAD, so you end up with NADH plus a proton. That goes to ETC. Have we lost any carbons yet from that fatty acid? No, all we've done is oxidize it. But we're in the matrix. So we're oxidizing, providing the electrons to ETC. So far we've basically got 5 ATP just by oxidizing. We haven't lost any carbons yet. The next step is the cleavage step. This enzyme, which is a transferase, essentially takes a CoA and adds it right here. So this is the cleavage step. So this enzyme uses CoA and adds it right here to this carbon. That allows this to be released. What does that look like? That's acetyl-CoA. If you add another hydrogen here. So that's what happens. CoA is added, acetyl-CoA comes off. How many carbons did we lose? 2. Acetyl-CoA has 2 carbons in the acetate. But we got acetyl-CoA. Now we have a C14 fatty acid that can do this. Here's our C14. Here's 1, 12 of these, so that's 13, 14. Now we have a 14 carbon fatty acid that has a CoA. So what does it do? Repeat. It's probably hard to see, but that's an arrowhead right there. So this fatty acid now goes up and goes through these steps again. Starts another cycle. Oxidation, hydration, oxidation, cleavage. Now we would have a C12. Goes through it again. Okay?
So is that why like short chain fatty acids are like more beneficial because you like use them, or like it wouldn't take as long to like go through them in theory or something?
Why would they be beneficial? For energy production, I don't know if I'd say they're beneficial. They might be able to be metabolized into other molecules. That might be beneficial. Absorption, they don't go through chylomicrons. But generally, chylomicrons can handle lots of long-chain fatty acids. So there might be other advantages. I'd say from an energy standpoint, not really.
So this goes through until all the carbons have been used up?
Yeah. So really good point. Maybe this will answer yours. How many times does it do this?
8.
In a fatty acid with an even number of carbons, which I'll always ask you that. I'm going to ask you to do this and do calculations. We'll always talk about carbons with even numbers. So it'll be a C18, a 16, a 14. In that case, every carbon becomes part of acetyl-CoA. In fatty acids with an even number of carbons, every carbon goes into acetyl-CoA. So how many acetyl-CoAs does palmitate generate? 8. How about a C18? 9. Okay. When I ask you to do the math, I'm also going to say it's a saturated fatty acid. Why does that matter? Because if it's unsaturated, you've lost some hydrogens. You don't have as many electrons. The math would be different. We're not going to go there either. So always assume it's even number carbons, saturated. Now here's where you get kind of the questions. Yep.
When we're going over this, do you want us to know how to draw those structures?
I would love that, but you don't have to for this exam. Yeah, that would warm my heart. But no, you don't have to. My heart's cold. Lots of things warm it. So that's that's an important point to remember, is that they all go to acetyl-CoA. And here's why. Remember, each acetyl-CoA that supports a rotation of the Krebs cycle can generate how many ATP? That's a long time ago. That was like a week ago. Every acetyl-CoA that goes into Krebs cycle can generate how many ATP? I said, this is a good number to remember. Oh, we forgot it. How many? 12. Right? Goes through, you get 3 NADHs, an FADH2, and a GTP. 12. So every acetyl-CoA you make, Krebs cycle gives you 12 ATP. So those are counted too. Okay, so here's one more thing on this. If we call this one cycle, we go, here's one cycle. Here's cycle 2, cycle 3. In the last cycle, let's say we have a C4. It splits in half and you get 2 acetyl-CoA. So, the number of cycles equals, this is a good note, the number of cycles equals the number of carbons divided by 2 minus 1. Because in that last one, it splits in half. If you don't believe me, write out C18, split it in 2, and you'll see. Okay? In the last cycle, it splits in half. So you get 2 acetyl-CoAs, but you don't need another cycle to get that. Right? So in other words, let's practice this big math. So on palmitate, how many cycles? This isn't fair because at 9 o'clock in the morning you nail this, but at 5:15 at night, 14, right? 7 cycles. Let's do the math real quick. Here's palmitate, C16. So we're going to say 7 cycles. So the number of carbons divided by 2 minus 1, 7 cycles. Trust me on this. Every time you go through a cycle, every time you go top to bottom, you get an NADH, an FADH2, so you get 5 ATP from that. Remember that? Every time you go through this, you get 2 here, 3 here. That's 5. So multiply that by 7 cycles, 35 ATP, just from oxidizing it. You get 8 acetyl-CoA. Each of those can generate 12 ATP. So you get 96. Add those up, that's 131. Okay, that's gross. That's overall total ATP produced. If you consider net, you got to subtract the 2 for activation. This is for adding that CoA as the fatty acid went through the cytosol. So for every C16 fatty acid, you get a net of 129 ATP. Does that sound like a lot? That's one fatty acid. 16 carbons. Let's think about a relative example. How does that compare to glucose? One of the things we say is, you know what, fat has more energy potential than glucose. Why? There's 2 reasons. Two main reasons. Yeah, like, can you think about, so let's say, let's kind of compare and say, boy, is it fair to compare 1 palmitate to 1 glucose? It's not, because the number of carbons are different. So let's say, what if we had a C18 fatty acid, 18 carbons, compared to 3 glucose molecules? Which one generates more ATP? Just guess. Probably the fatty acid. Why? Now, let's say we have three glucose molecules, carbons, versus a C18-0 fatty acid. Do the math. This is a good practice. Do the math. What's the maximum number of ATP you can get from glucose? 38 times 3. Can be a little over 100. Now the C18. You can see right now it's going to be more than this. You see the fatty acid generates more. And there's 2 reasons. One is, if you think about the structures, which has more hydrogens available to provide electrons? Fatty acids. So one of the reasons that fatty acids have more potential energy is their molecular structure. Their molecular structure contains more potential electrons for ETC. Right, because glucose has oxygen in its structure. That's not a source of electrons. So fatty acids, their molecular structure contains more potential electrons for ETC. Second reason. Can we say, don't write this yet, sorry. Can we say that every carbon in glucose becomes part of acetyl-CoA? Why not? Where?
The bridge step and also
You're already just from glucose to acetyl-CoA. Do you lose carbons anywhere? So look at it this way. Yeah, look at it this way. So if I have a glucose molecule, right? If I have glucose, 6 carbons. If every carbon became part of acetyl-CoA, how many acetyl-CoA would I get? How many do I actually get? I could go glucose. It's not funny. Two pyruvates. And each one of those pyruvates becomes acetyl-CoA. You lose carbons that don't become part of acetyl-CoA. What happens to them? They're decarboxylated in the bridge step. So it's not as efficient in using its carbons to make acetyl-CoA. So you don't get as many acetyl-CoA out of it either. So less electrons available and fewer acetyl-CoA. Okay, so you have more potential energy in fatty acids. So why don't we just use those all the time? One reason is, yeah, you can't, you have to have oxygen to get the energy out of fatty acids. Glucose you don't. Do you guys want to keep going and then we leave like 10 minutes early, or do you want to take a little break now and come back? Don't worry about me. I'm fine. Okay, let's keep going. Okay, I'll keep going. Okay. Everyone got that? So I'll have examples in the study guide, but be ready to do that on the final exam. Do those calculations for ATP production and the comparison to glucose. Now, there's an old saying. Here's a let's go down history. There's an old saying in metabolism, and that is that fat burns in a carbohydrate fire. Have you ever heard that? Now you have. And there's other ways. Some people say fat burns in a carbohydrate flame. So if you just think about the phrase, what it means is they're integrated. Their metabolism is not exclusive from one another. There's overlap. And one of the things I think that people don't realize is carbohydrate actually helps us burn fat. And depending on what you're looking at on the internet, some people would die before they admit that. Carbohydrate helps fat oxidation. Okay? In other words, it's okay to have carbohydrate. I scanned a guy this afternoon on the DEXA. He reached out to me through a dietitian that I know a little bit. And she said, hey, you know, this guy wants to get his body fat done, blah, 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 and his percent body fat. I said, okay. So he came in, and he's in the prime of his life, about my age. And I got to keep thinking that. Very lean, very good shape. Right? And so I was talking to him about stuff, and anyway, I said, so of course I have to ask this question. So, are you on a ketogenic diet? He goes, no, not at all. I eat plenty of carbohydrate. I'm like, oh, okay, good. right? Sometimes I'm like, so a few weeks ago I scanned another guy. Not great. Not great body composition numbers. Are you on a ketogenic diet? Yes. Oh, okay. So I'm like, okay, so where are you getting your information? Oh, I get it from here, I get it from there. I'm like, oh, okay. The other person's working with a dietitian. I'm like, okay, that's a very small sample size, N of 2, but okay, that's good. So, and he realized that, you know, carbohydrate helps fuel his exercise and it can help with body composition and all of that. So we're going to look at how and why, how they overlap. And part of this has to do with how do we generate ketones and enter ketogenesis when carbohydrate's limiting. I'll show you the key reaction that kind of sets us up for that. So how does carbohydrate help burn fat? Well, the oxidation of fatty acids can produce large amounts of acetyl-CoA. We've seen that, right? Acetyl-CoA has to combine with oxaloacetate in order to enter the Krebs cycle. Oxaloacetate is normally from glycolysis and pyruvate, if necessary. If oxaloacetate is low, acetyl-CoA molecules accumulate and they actually combine and they form ketones. So keep that in mind. Let's kind of visualize this. So I think a lot of times when we draw a Krebs cycle, we just go, oh, okay, there's acetyl-CoA, it turns around, and then here comes turns oxaloacetate, here comes another acetyl-CoA, and we do the math just kind of like that. But imagine this, the scenario that we just went through, and I said, well, you know, if, for example, you're oxidizing significant amounts of fat, carbohydrate actually helps us burn that fat. Bear with me, I draw slow. So let's see, where were we? Here's acetyl-CoA. And let's say this is a fatty acid that generated the acetyl-CoA. And now here's another fatty acid that generated the acetyl-CoA. I'm not going to do this over and over again, but I think I can do this with 4 times. Here's another acetyl-CoA. And here's another acetyl-CoA. Let's say, for example, for some reason fat oxidation has gone up. Let's say I've eliminated carbohydrate from my diet. Does fat oxidation go up? Yes, that's true. So let's say, for example, carbohydrate's limiting and I'm generating lots of acetyl-CoA. Every one of these acetyl-CoA molecules has to combine with oxaloacetate in order to go into Krebs cycle. So we can go, okay, this combines, then we get citrate, right? I think that's right. This goes like this, we go around. Okay. What about this one? Same thing. It's got to have oxaloacetate. Got to combine all this. All of these do. What happens when there's this significant flux of fatty acids going into a cell? Acetyl-CoA is in massive levels, so then rather than just looking at it this way, let's say we have 1,000 acetyl-CoA molecules. Every one of those has to have oxaloacetate to go into Krebs cycle. Let's say we've gone from a static state of a balance between oxaloacetate and acetyl-CoA, and now a ton of acetyl-CoA has entered into a cell. The system can be overwhelmed. If we have carbohydrate, we can do this. And a lot of people we don't pay a lot of attention to this reaction, but it's up here. So far, most of the time you say, oh, pyruvate can become acetyl-CoA. Pyruvate can also become oxaloacetate. You can go from 3 carbons to 4 carbons. There's a enzyme that does that. Where do you get the pyruvate? Glucose. As long as you have glucose, some of the pyruvate can be converted to oxaloacetate. That allows you to now take more acetyl-CoA and partition it and push it into Krebs. What if you don't? If you don't, this is what happens. If, for example, you're low on glucose, glycolysis is minimal, so we're not able to go like this. To go to citrate. Say we're short here. We can't do this. So now we have acetyl-CoA molecules that have accumulated. In that scenario, this is what happens. The acetyl-CoA molecules combine. Now, rather than this acetyl-CoA condensing with oxaloacetate, it condenses with another acetyl-CoA. Guess what that makes? Ketones.
So on a ketogenic diet, people are usually consuming like 15 to 20 grams of carbs. So what happens to those? What's their main priority?
That glucose?
Yeah.
It kind of depends. Let's see, but initially that glucose might cause a little bit of an insulin response, and right when they eat it, it's going to go into more insulin-sensitive tissues and stay. If it does that, it could end up in maybe muscle fibers and fat cells. But some of it will distribute. If you imagine now that small amount of glucose being, kind of diluted in between all the tissues, it doesn't have much of an effect metabolically on any of the tissues. It doesn't cause a big insulin increase, and so it's kind of distributed through all the tissues and not really metabolically affecting any of them significantly.
So, isn't like the minimum grams of carbohydrate 130?
130, yeah, that's RDA.
So, like, is this diet considered dangerous then?
Which one?
The ketogenic diet?
We'll go through all this. I'd say it depends on the scenario. It depends on the person. But it can be. And we'll talk about how. So far we good here? Now the other thing is, remember we're saying here, okay, if we do have citrate, we can go through here, we can get to oxaloacetate can rotate through. Here's the other part of the equation. In this scenario, if you're consuming really low amounts of carbohydrate and glucose is being depleted, what are two things we're doing in order to maintain blood glucose? Gluconeogenesis, hepatic glycogenolysis. If, for example, a person's on a situation where they haven't consumed much carbohydrate over a period of time and hepatic glycogen is depleted, gluconeogenesis is elevated. And you guys on your exam, one of the things you said was, pyruvate kinase bypass. Some of these molecules are actually pulled from Krebs to make glucose. So in some of these scenarios, we're not even just going around and getting back to oxaloacetate and having that for acetyl-CoA. Some of these Krebs molecules are being pulled out to make glucose. And that's kind of what this is showing. What kind of molecules are these? Those are all amino acids. This is the liver. Some of these amino acids are coming from other tissues. So in a really low carbohydrate diet, gluconeogenesis is elevated. Main substrate for glucose and gluconeogenesis, amino acids. Amino acids are the main carbon source for gluconeogenesis, right? And that's what's happening in the liver. The liver is the tissue that does that. So imagine some of these amino acids are coming from other tissues. In that scenario, skeletal muscle catabolism can be elevated to provide amino acids for gluconeogenesis. So some of these amino acids are coming from outside the liver and now going through the pyruvate kinase bypass, going to oxaloacetate, and rather than combining with acetyl-CoA, they're going this way to glucose.
In a low-carb diet, do you know like what percent of the energy is coming from fat oxidation versus amino acids? Like when do you start breaking down muscle?
Very quickly, if you a few hours after a meal. As soon as a hormonal profile changes, insulin's anabolic. Some of the other hormones like cortisol and some of the other ones that come along as that fast extends start breaking down tissues. especially muscle. So it doesn't take that long for that to happen. The longer you go without carbohydrate, the more it's accentuated, and the more of it's occurring typically.
So it will attack your muscles first before the fat cells? Like we're just sitting here.
Well, yeah, it's a combination. You are oxidizing more fat, but you're also increased gluconeogenesis, so you're oxidizing and using more amino acids for glucose and energy. So it's a combination. Mm-hmm.
So in the ketogenic diet, is it like difficult to get sufficient like amino acids in the diet to avoid gluconeogenesis and like metabolism in the muscles?
So and we haven't talked about this yet, but there's not really a storage molecule for amino acids. So once they come in, they're dealt with. They come in, and we'll talk about this. They go in through the portal vein. They go to the liver. The liver just degrades a lot of them to give us metabolic flexibility in that case. So there's not really a way to take in a bunch of dietary protein to support this. Those amino acids are dealt with immediately. They're either stored in muscle as skeletal muscle. In that case, they're a functional tissue that we have to break down in order to get them for glucose. Yeah, so we don't have a triglyceride or a glycogen-like molecule for amino acids. It's kind of sad, but that would have been great.
If someone did the ketogenic diet, also like not eating and like a large amount of fat, like more fat, they just like made it a high protein diet, would the skeletal muscle degradation like still be as severe?
Yeah. It is, so ketogenic diet is a high fat, high protein diet. Yep. So it's a lot of those. Yep. Now, I'm not saying that people shouldn't be conscious how many carbohydrates they eat. I don't want to say that. I don't want to say, hey, carbohydrates are good, eat all you want. It needs to be based on individual kind of needs. And our basic need is the RDA. Brain and central nervous system. So I would say we start with about 130 to 150 grams. That's your baseline. That's if, you want to get through the day. Physical activity requires more. And that physical activity can involve walking or running, especially if it's exercise. You need carbohydrate to support that exercise. So in that case, you're kind of adding to that. So I'm not saying everybody needs to get 60% of their calories from carbohydrate. Some people can eat quite a bit less, but you want to make sure that a person's eating adequate amounts to avoid the kind of catabolic scenario where you're breaking down tissues to get amino acids for glucose. Remember, that's part of that definition I said, to avoid ketogenesis. And one more point. Are we making ketones right now? Yep. We generally always make some ketones. So if a person's on a ketogenic diet, they say, oh, I'm on a ketogenic diet. Well, we're kind of all in ketogenesis. The difference is ketosis. Ketosis is when they accumulate. And that's kind of progresses to that. And so I'll give you some numbers on ketones and how they accumulate during fasting and starvation coming up. But typically we make some, but they're minimal. Okay? So here's one of the points of this. Why is the liver doing this? Well, the liver's doing it because it has to. It is, in this case, it has a minimal carbohydrate influx. And one of the important roles of the liver is to provide fuel to other tissues. Right? So in this scenario, here's what the liver is doing. Okay? In this scenario, the liver could be depleted of glycogen. So what does it do? Continues to do gluconeogenesis. It's impossible for the liver to make enough glucose to supply the demands of the body. So the liver makes another fuel source, and those are ketones. So that's what it's doing here, and I'll show you the diagram of this in a second. So acetyl-CoAs combine to make acetoacetyl-CoA. That is not a ketone. It's a precursor for ketones. from that, ketone bodies are made. The ketones leave the liver and go into the blood. They end up in other tissues too. Like if you use keto sticks, you can measure ketone bodies in your blood or your urine. They'll be in both. The ketones go to other tissues to provide energy. So the brain can use ketones. Muscle cells can use ketones. So in this case, the liver's providing an alternative fuel source for other tissues. And it's also doing gluconeogenesis. Now, under what conditions can you guess? Let me show you one more. You probably need a little bit more information. Here's ketogenesis. Here's our acetyl-CoAs, and here's two. And I said, okay, these combine. When they combine, one CoA comes off. Here's acetoacetyl-CoA. That's not a ketone, but it becomes acetoacetate. Here's our first ketone body. There's no CoA attached. Acetoacetate is one of them. Acetone is another ketone. And beta-hydroxybutyrate is considered another ketone. So these three in purple, that's purple, right? These three in purple are considered ketone bodies. So now look what happens to these. These interconvert. These go back and forth. This is unidirectional. Once we get acetone, it doesn't come back. This is a decarboxylation reaction. I'll show you that in a second. If someone is fasting for a long period of time, or they're starving, or they're making ketones, some of it ends up in acetone, some of it they expire. You can actually kind of taste that if it's you, or you can sometimes smell it on another person's breath. It has kind of a distinct odor. And so that doesn't revert back. So this is a minimal percent of those ketone bodies. Okay, but look what happens. Acetoacetate converts back and forth, but acetoacetate can essentially go back to acetyl-CoA. So the liver puts these ketones into the blood, tissues take them up, they can reverse back to acetyl-CoA. Can they get energy out of that? Yeah, they can run it through Krebs. In order to do that, let's think about the brain. This is a fuel source for the brain. So ketones can go through that epithelial layer, that blood-brain barrier. Ketones can go into the brain. They can revert back to acetyl-CoA. Acetyl-CoA can combine with oxaloacetate into the Krebs cycle. In order to do that, it helps the brain to be getting glucose from the blood, because now the brain can go glucose to pyruvate to oxaloacetate. So this diagram is showing the liver, but now imagine what I just said. Let's say this is the brain and glucose is going in. It can run through glycolysis, become pyruvate, then oxaloacetate, and it can combine with acetyl-CoA that came from ketone bodies from the blood. So the liver's kind of is putting two fuel sources into the blood that support each other for fuel sources in other tissues. That's one of the reasons the liver is still making glucose. And of course, red blood cells in some tissues have to have that glucose. Yep.
And acetyl-CoA can't get through the blood-brain barrier?
Correct. Yeah, you won't find it in the blood. Yep. Got that? Here's what they look like. The first one is beta-hydroxybutyrate. There's its structure. 4 carbons. Acetoacetate. 4 carbons. Acetone, 3 carbons. Decarboxylation, CO2 comes off, and you end up with acetone. Okay, these are considered the ketone bodies. Are they all ketones? No, right? Here's ketone. Here's ketone. So why do we include this one? Yeah, because it readily converts. So it's included as one because it's converted easily to one of the actual ketones. So we include all of those. Kind of one of the interesting points of all of this is if you measure these in the blood, beta-hydroxybutyrate is the highest one. And here's an example of that. So one of the things I said was, and I have values. I don't think it's that important. I'll just tell you these values. So let's look at 0 time point. Let's say before a person starts kind of a starvation scenario. If you measure them in the blood, you find trace amounts. As that fast goes from kind of day 1 into starvation, the ketones start to accumulate more and more. So remember, blood glucose is going to be low. Hepatic glycogen, once it's depleted, really changes a lot about metabolism, including it really ramps up ketone production. And if you look at these concentrations, you can see how they go up, and you can see which one's the highest one. Beta-hydroxybutyrate is higher than acetoacetate. And you can see, though, it kind of goes up and kind of peaks. So after a few days to about a week, the ketones are a significant energy source. Tissues actually run pretty good on them. So it's a pretty good alternative energy source. The problem is it's expensive. You're in the scenario where you are doing lots of gluconeogenesis. That requires energy, and it also can remove skeletal muscle, so that can have a metabolic effect as well, and a physical effect, obviously. So our body, this is definitely survival mode, but our body has a way of surviving starvation. One of the other reasons it's doing this is to minimize skeletal muscle breakdown, because we're kind of providing an alternative energy source other than just glucose in this scenario. So you can minimize skeletal muscle loss because you're getting more energy out of ketones than you are in glucose in that case. So it's kind of a way to minimize tissue loss and survive.
So people who were on a ketogenic diet and then go back to like a normal diet, do they gain a lot of weight back rapidly? Like what happens physically?
It depends. I think they can for 2 reasons. One is sometimes their diets are so different. If they take in now different fuel sources, sometimes there's a hydration situation as well. Not only are they consuming maybe more fruits and vegetables and other good sources of electrolytes that can help kind of rehydrate, the addition of glycogen to tissues absorbs water. So you get kind of a water flux as well. In addition to now sometimes if their metabolic rate is slower than it was, and now they go back to eating more calories or the same number of calories, they'll tend to gain weight because the calorie differential. I think I would never do this, but it doesn't surprise me that people do. They've done quite a few studies on this. What happens to body composition, metabolic rate, and all of that when you switch from one to the other. And bottom line is, I think I mentioned this before. If you look at, and I tell you this because years ago it was called the Atkins diet, and now we call it the ketogenic diet. And most of the studies back then showed, for rapid weight loss, like after a few weeks, you'll tend to lose more weight on a ketogenic diet than you will on a healthier, high-carb diet. If you look at those people after 6 months or a year or longer, the higher carbohydrate diet, they tend to retain or maintain weight loss better. And part of it has to do with they're not doing that. That's one of the for me is kind of that. But I understand where people want to, minimize carbohydrates and lose weight. Absolutely, losing weight, maintaining ideal body weight, all of that is not easy. I mean, it's not. I trust me, it changes, especially too with age. But you also, it's not easy to do. So I don't blame people for reaching out for something that has worked for me before. I just think that going back and forth it over and over again is a problem.
So if you're eating enough calories to not lose like your muscle in a ketogenic diet, is there really like is there harm to it to your body, or is it just the fact that people don't usually last as they go on and on?
So good question. So let's look at this, and then we'll end up on this today. So about 1 more minute. So when ketones accumulate, we tend to call it ketosis, and they're accumulating in the fluids I talked about before. So this is an abnormal rise in the concentration of ketone bodies in the blood. So, for example, in conditions of starvation or a very low carbohydrate diet or diabetes mellitus that can occur, this is when the carbohydrates aren't available or they can't be used. So, if a person's insulin resistant and the glucose is not going into the tissues, it can't be used metabolically. So that can promote ketone production as well. For most people, it's not a problem. The ketones are weak acids. So they do tend to pull the blood pH down. So it can lead to ketoacidosis, where the ketones are actually dropping the blood. Most people have buffering systems that are fine and don't have to worry about that being life-threatening. Some people, though, it does become problematic. In some cases, if a person's diabetic, and that can be a complicating factor for this, but even in that case, most of the time the ketones are not going to be life-threatening. I think it's more about some of the other issues that come into play. So if people say, oh yeah, it's perfectly safe, it might not be potentially really harmful from the ketoacidosis, but there's other aspects to it. I'd say long term, I wouldn't say it's a good scenario. We spent a lot of time on that, huh? We good there? You guys get a lot of questions about that ever? Or you see a lot of stuff about that? Okay. Did you talk about it in other classes? Not really? Okay. Okay, I don't think we'll talk about it again in here. So. But if you have any questions, let me know. Thank you, guys. I'll see you next time. So tonight I'll post the protein lectures and a bunch of the study guide stuff.
Kind of a weird one, not really like in the scheme of this class. But do anything about like the difference between marijuana and cannabidiol? Because I guess I could like set the stage. It's not for myself. My grandma's on tons of meds. She's like 87, so things are rough. She just has like constant body aches all the time. And so one of my uncles is like slightly hippie and was like suggesting cannabidiol oil or like edibles because it's not THC, so it's like a muscle relaxant. But would that possibly contradict with lots of other